So here's the notation we use for antiderivatives, and it should be familiar. We call it the integral from f of x. The thing you want to say that this means is it's the antiderivative of f of x. But as it turns out, two functions can have the same derivative. To say using the word the here is bad. There isn't only one antiderivative of f of x. There are lots of them. Math hates a question that has more than one answer. We want to be able to use the word equals. And if this thing equals more than one thing, like the whole idea of equals breaks down. Like you've had a section in some algebra class about functions and what is a function. And the reason we make functions what they are is when we talk about a thing, we want the thing to be specific. It might not exist. Mathematicians are fine with a thing turning out not to exist. We hate when it turns out to be more than one thing at the same time, because all the times we used equals about that thing are suddenly all suspect, and we don't like that. So instead of saying that the integral of f of x is the antiderivative of f of x, we say that it is all antiderivatives of f of x. And we'll say what that means in a second. To clarify a little bit more terminology about this, this is an indefinite integral. The reason it's an indefinite integral is the lack of the little subscripts. When you have an integral from here to here, this is a definite integral. A definite integral is just a number. It's really easy to understand what its existence is. An indefinite integral is more complicated than a number. It's a function, and it's even more complicated than that because it's not just a function. It's lots of functions. So the reason that it's this complicated is, like I said, it turns out 1/3 x cubed isn't the only antiderivative of x squared. Can you think of another one? Pause the video. Think of another for a second. I watch a lot of videos that say pause it and think about it, and I never pause it and think about it. One of them is 1/3 x cubed plus 1. What's the derivative of that? The derivative of that is 1/3 times 3x squared plus 0. Oh yeah, it's also x squared. Or 1/3 x cubed minus 8, or 1/3 x cubed plus pi squared over 6. All the antiderivatives of x squared are basically the same. They're only off by a constant. So the thing we do when we write our answer for what is the integral of x squared is the way we write our indefinite integral of x squared dx, is 1/3 x cubed plus c. The plus c is representing the fact that c could be any number, and you will still have an antiderivative. And every antiderivative, it turns out, it's not obvious right now, but we can verify it without too much work, I don't think we ever will, that every antiderivative of x squared is of this form for some correct choice of c. The c here is called the constant of integration. And it's a dumb thing you have to remember to put at the end of your integral problems, or else you lose a point. It's sort of the way to think about it. It's a big deal because it's the difference between giving one solution and giving all of the infinitely many solutions. But it's a goofy thing to have to remember. So let's state some rules of integration. We've seen a bunch of rules of derivatives. I will write them down real quick. Our first two big meta rules for derivatives are the ones we don't think about that much. They were the easy ones. If you have a constant out front of a function, then the derivative is still the same derivative, but with the constant out front. And that translates over to integrals totally fine. If I have a constant in front of a function that I want to integrate, you're allowed to pull the constant outside of the integral and just integrate the function. Whenever you find what that function is, that's what it is. Oh, also this capital C is different from the plus C that comes up in the answer. Like, maybe I should use a lowercase c. Same deal for two functions added and subtracted. If I have the two functions that I know with a plus or minus in between them, then I take their derivatives one at a time and leave the plus or minus between them. Same deal for the integral. The integral of two things added or subtracted is the sum or difference of the integrals. This would sort of suggest having two different plus c's, which is fine. A constant plus a constant is still a constant, but it looks goofy if you write that. You usually only write the 1 plus c at the very end of the problem. And then we got the power rule. The derivative of x to the n was n x to the n minus 1. I think about what I did for x squared. The integral of x squared was x cubed, but you got to divide by 3. I can get that rule pretty well straightened out. I needed to add 1 to the exponent, and then to cancel what's going to happen when I take the derivative, I need to divide not by the old number, but by the new big number. Think about the derivative of this. The n plus 1 is going to come down. It'll cancel with that. I'll be left with n. That's what I wanted. I wanted x to the n. The integral of x to the n is 1 over n plus 1, x to the n plus 1, plus c. This rule has a fraction in it. When someone hands you a rule with a fraction in it, you should always have in your mind, wait, what if we divide by 0? There's a version of this rule that has us trying to divide by 0, and we can't divide by 0, so that version of the rule must have a problem. For the moment, we'll just add an if n is not negative 1. What happens if n is negative 1? If n is negative 1, then I'm trying to integrate x to the negative 1. Like this is the missing version. What does x to the negative 1 mean? It means 1 over x. Do I know a function whose derivative is 1 over x? Why, yes, I do. It's the natural log of x. So the integral of 1 over x is natural log x plus c with an asterisk. Let's talk about that asterisk. There's a weird thing that's been going on when we take the derivative of natural log that we haven't thought about too much. Natural log looks like this. Right? It's only defined to the right of the x-axis. When I write the derivative of natural log 1 over x, that exists on the right and it also exists on the left. Is that a problem? Well, it wasn't a problem when I was taking the derivative. When I try and take the derivative of a function, like the formula 1 over x gives me both branches of this, but when I'm trying to take the derivative of natural log x, I must have only been talking about this branch, because that's the only place I would ever ask for the derivative of natural log, right? When you give back more answer than the question asked for, that's not really a problem. Now that we're doing integrals, though, now the question is, what's the integral of 1 over x? And now, so my question now exists on both sides, and this thing I thought was the answer, natural log x, only exists on one side. What is the missing part of the answer? Like, now my question existing on both sides needs an answer that exists on both sides. But it turns out to be natural log negative x. What's the derivative of natural log negative x? I know the chain rule, so I can do this. It's 1 over, leave the inside alone, times the derivative of the inside. What's the derivative of negative x? It's negative 1. Hey, this negative cancels with that, and I get 1 over x. Natural log negative x is the mirror image of natural log x that exists on the other side. So the integral of 1 over x needs to be a combination of natural log x and natural log negative x, where you use one on the right and the other on the left. Well, it turns out we know the name for that. If you want to use x for positive values and negative x for the other values, you call that absolute value. The moral of the story of that slide is that the integral of 1 over x isn't just natural log x, it's natural log absolute value of x. And like the plus c, that's mostly going to be a thing you think of as a thing you got to remember, you lose a point. It's not a deep thing, but when you're trying to plug in, if you're trying to take natural log of a negative, there's a good chance that's the thing you're missing. If you're doing the power rule and you find yourself trying to divide by 0, there's a good chance that's the missing thing. Like, you catch yourself making these mistakes when you see yourself taking natural log of a negative.